Let's wait for 5 minutes before we start this session. Okay, so today we will be discussing the questions that were given in the assignment sheet of week 10 that involves mainly the problems related to the change of variable, precisely the Jacobian matrix and its determinants. And further, we will look at some problems that involves the nonlinear space. So let's start with our first problem. Question number 1. It says that consider the change of variable the change of variable. We take x to be u square minus v square and y to be 2uv. Then the determinant of the Jacobian, and we denote the Jacobian as del xy upon del uv when we translate from xy to uv, and this is equal to part A 0, B u square plus v square, C u square minus v square, or D 4u square plus 4v square. So let's just recall how we calculate this Jacobian. We know that when we transfer, so basically when we make change of variable from xy to uv, where x is some function of uv and y is some function of uv again, in that case we calculate the Jacobian as del xy, and in fact its determinant is actually the determinant of the matrix del x by del u, del x by del v, del y by del u, del y by del v. So I would like you to evaluate this determinant first, then we'll check whether you're able to get the exactly same. All you need to do is just differentiate this with respect to u and v separately, and again with respect to differentiate this y with respect to u and v, and find this determinant. I'll wait for 2 minutes. Please solve yourself, and then we will discuss. Okay, so since x is equal to u square minus v square, we have del x by del u equals to 2u. Del x by del v is minus 2v. Then again, since phi is 2uv, that gives us del y by del u 2v and del y by del v as 2u. So the determinant of the Jacobian matrix is equal to the determinant of the matrix 2u minus 2v, 2v, 2u. And we all know how to evaluate the determinant. This will be 4u square plus 4v square. So therefore, option D is correct. I hope this solution is fine. If you have any doubt, you can ask. Or else then we'll move to next question. Okay, then if there is no doubt, let's move to question number 2. Let A be a matrix. Let A equals to A, B, C, D be an invertible matrix. Consider the change of coordinate. Matrix defined by A uv is equal to xy. Then the Jacobian the Jacobian that written out by del xy by del uv is A or A inverse or A transpose or minus A. So here we are given the change of coordinate is something like this. So what does this mean? It means that our xy are now equal to A times uv, which is A is just a matrix A, B, C, D, and we multiply this matrix with the vector uv. So this gives us AU plus BV, CU plus DV. That means our change of coordinate is in such a way that now our x is equal to AU plus BV and y is equal to CU plus DV. Now that gives us that our Jacobian, this is equal to del xy upon del uv. This is equal to the matrix del x by del u. The first coordinate will be del x by del u, and when we differentiate this with respect to x, with respect to u, we get A. Then with respect to v, this is B. Then with differentiating this y with respect to u, we get c. And again with respect to v, we'll get d. So this is exactly equal to a. Therefore, we get that our Jacobian is equal to a. And hence our option A is correct. I hope this solution is fine with everyone. If you have any doubt, you can ask at any step how we did whatever we are doing. Okay, so if there is no doubt, we can move to next question. Question number 3. It is almost an application of question number 2. Whatever we did used previously, we'll be using that. State whether true or false. Suppose we consider a coordinate transform from xy to uv such that the determinant of the Jacobian Jacobian is 0, then the transformation is not invertible. I would like you to think first. I'll give some time. Think about it. Okay, so now since we are given that the Jacobian determinant of the Jacobian is 0, that means the determinant of the matrix, or instead, let's start with looking at the transformation. Suppose we had x equals to some function of uv and y is some function of uv again, then we get 0, which is equal to determinant of the Jacobian matrix del xy upon del uv, which is equal to del f1 by del u, del f2 by del del v, del, this is f1 na, del f2 by del u, del f2 by del v. Now if I define a function f from R2 to R2 such that f at any point xy, this is equal to f1, sorry, uv, so that it's clear for you to understand. uv, this is equal to f1 uv, f2 uv. Then we know that by inverse function theorem, I'll just recall this inverse function theorem for you, or at least the part that we need. By inverse function theorem, since the determinant of the matrix J, where this is 0, where J is just del f1 by, that means the derivative of first coordinate function with respect to first variable, first coordinate function with respect to second variable, second coordinate function with respect to first variable, and second coordinate function with respect to second variable. Now if this determinant is 0, then we know that the function need not be, is not locally invertible. In fact, when the determinant is non-zero, at that case, we can say that the function is locally invertible. That means in that case, we are able to find some inverse, which will be its inverse for locally, at least in some neighborhood of the that point wherever the Jacobian is non-zero. But here we are given that this determinant is always zero. That means this Jacobian this determinant is zero for all uv. That means it is nowhere non-zero. That means it's nowhere locally invertible, and hence it will be always in not invertible. That means yeah, since this determinant is zero, the function f is not invertible, and that's what our transformation is. By the coordinate transform from xi to uv, we mean this function is not invertible. I'll just write the inverse function theorem for your reference. Since by inverse function theorem, I would like you to go through this theorem in detail. It is very good, very important result. If f is a function from, suppose, Rn to Rn, and J is the matrix. Now, since f is from Rn to Rn, that means f is something of the type f1, f2 up till fn. And then we define this J as, again, del f1 by del x1, if suppose x1, x2 up till xn are the variables. So del f2 by del x2, and sorry, del f1 by del xn. Then similarly all other rows, del fn by del x1, del fn by del x2, and so on up to del fn by del xn. Now if this is the matrix, and if the determinant, if determinant of J, and we can write this as again a function of x, J x, which can be written as x1 up till xn. This is equal to this. And if at some point this determinant is non-zero, then we say, for some x naught and Rn, then this function f is said to be locally invertible. That means we are able to find its inverse in at least in a neighborhood of x naught is locally invertible. That's the main essence of this inverse function theorem. Now, since in our case we are getting that this determinant is zero always, that means there is no point where the function can be even locally invertible, and hence it will never be invertible. And that's what was given in the statement. No? They were saying that if this determinant of the Jacobian is zero, then the transformation is not invertible, and yeah, we are able to show that this is true. Therefore, the given statement is true. I hope this is clear how we use the inverse function theorem. And in fact, as I was saying, that it is kind of an application of previous problem. Suppose if this function f1, f2 were some linear functions. So in that case, they would have been, say, some au plus bv, and this would have been some cu plus dv. And in that case, the Jacobian would have been eventually be equal to the same matrix A. And since The Jacobian is determinant of Jacobian is 0, determinant of A is 0, and hence this type of linear transformation, this cannot be invertible if A is not invertible. We all know that, because the linear transformation and the matrix corresponding to the linear transformation are equivalent. If the matrix is not invertible, then we say that the transformation is not invertible as well. Yeah. And for general case, we use this inverse function theorem. I hope this is clear how we are using the inverse function theorem here to eventually get that. In this case, the transformation, it need not be linear. The transformation is not invertible. Please go through the solution again. I'll wait for 3-4 minutes. If you have any doubt, you can ask. Okay, so if there is no doubt, we can move ahead. Next, we'll look at some problems related to norm on Euclidean space. Question number 4. Consider the Euclidean norm and the supremum norm. Will define how they are specifically given, and the supremum norm denoted as this on Rn, defined as this Euclidean norm is equal to under root x1 square up to xn square, and this supremum norm is equal to maximum of mod x1, mod x2, and so on. Then, yeah, this happens for every x which is an n tuple, xn and Rn. Then, which of the following inequalities is true for all x in Rn? Option A, norm, the Euclidean norm is less than equal to the supremum norm. Then they are saying that this Euclidean norm is less than equal to 4 times the supremum norm. Then they are saying that this Euclidean norm is less than equal to supremum norm upon n, and the D part is Euclidean norm is less than equal to root n times supremum. So firstly, before starting this problem, I would like you to notice that if suppose in this case our n was equal to 1, so what would be our Euclidean norm? This is just under root x1 square, which is equal to mod x1. And yeah, that's what x is x1 only. And I hope I am audible and still visible. Okay. Um, I'm sorry for the disturbance. I thought I got disconnected. Okay. Yeah. So in that case, the supremum norm for n equals to 1 will be the maximum over, again, just mod x1. That means all of them are just equal to the mod x function. So I would like you to understand the fact that this norm is kind of generalization of modulus function. That's it. So it is kind of generalizing what the modulus function does for the higher dimension spaces R, such as Rn. In fact, we'll see some other nonlinear spaces as well. So, okay, let's solve this problem first. So here, let's say what is this Euclidean norm square. So this is mod x1, sorry, not mod, it's just x1 square, no? x1 square plus x2 square and so on up till xn square. Now, since this the supremum norm, this is maximum of all these entities, mod x1, mod x2, so on up till mod xn is greater than equal to mod xi, and this happens for every I. You can take 1 to up till n. Of course, it will be equal to sum of some xj, but still, in that case, also greater than equal to will work. So that means this mod x supremum norm is square is greater than equal to mod xi square, or this can be written as just xi square because square is always positive. This happens for every I up till from 1 to n. That means this mod the Euclidean norm, which was equal to x1 square up till xn square. Now these all xi's are less than equal to the supremum norm square, so I can write it that less than equal to square, so on x infinity square. So this is just n times the sup norm on the supremum norm. That means the Euclidean norm, just taking square root both the sides, is less than equal to under root supremum. This was our option 4. Therefore, option D is correct. I hope this solution is fine. Please go through it once again. I'll wait for 5 minutes. If you have any doubt, you can ask. Okay, so if there is no doubt, we can move to next question, which is kind of similar, just the other side of the inequality. Okay, we have question number 5. Consider the definition of the Euclidean and the supremum norm as given in the question number 4. Consider the definition of the supremum and the Euclidean norm on Rn as given before. As given before, then which of the following inequalities is true? Which of the following inequalities is true for all x in Rn? And the inequalities are as follows. Sup norm is less than equal to the Euclidean norm. N to the power 1 by 4. Sup norm is less than equal to the Euclidean norm. Sup norm is less than equal to Euclidean norm by n, or just none of these. So earlier we were looking for the upper bound of this Euclidean norm. We were just trying to find what it is lesser than equal to, and in this case we'll look for the upper bound of the this sup norm. So yeah, that's again not a tricky task. Just you need to notice the definition of the sup norm. Now the sup norm, this is equal to maximum of all mod x1, x2 and so on up till xn. Now obviously this will be equal to sum of xj. I mean, when we have n terms and we look for the maximum, it will be sum of the term from all those n terms now. So this is equal to mod xi for some fixed for some fixed I. Obviously, then and of course this will be less than equal to x1. I should write it as, yeah, this will be less than equal to x2 square up till, yeah, instead, for a better understanding, I should write what is mod xi square, mod xi. This is equal to under root xi square. So obviously this will be less than equal to, I can add some of the positive terms. Adding some of the positive terms will make it bigger, and of course in between it will have will have this xi till xn square. And what is this? By definition, this is the Euclidean norm. Sorry, 2. So therefore we get the sup norm is less than equal to the Euclidean norm. And in fact, yeah, from here we can say that this option A is correct. And in fact, from above both the problems, question number 4 and 5, we can conclude that this sup norm is less than equal to Euclidean norm, and this is less than equal to root n times sup norm. So this is a very important inequality when we are studying the non-linear space, in the context of non-linear space. I'll now, since we are done with assignment problems and still we have some time, I would like to discuss some more problems related to the non-linear space, so that this idea of norm and what is a non-linear space, that will be a bit clear for you. So firstly, go through the solution again. If you have any doubt, you can ask. Then we'll move to some other non-linear spaces. We'll discuss the notion of sequences in non-linear space and some other norm as well. Okay, so if there is no doubt, we can move ahead. We'll look at some other norm and discuss the basic properties of normed linear space. So this will be question number 6. Let n be greater than equal to 2, be an integer. Let m n r denote the space of all n cross n matrices with real entries for A belonging to M and R. We define what we call the norm. This is something related to Euclidean norm. That's why we make this notation as E. This is equal to summation ij from 1 to n mod aij square to the power 1 by 2, where this A is n cross n matrix, aij n cross n with real entries. Let's firstly show that this is actually a norm. So yeah, we'll start with basic definition of norm linear space and how do we define a norm. What do we mean by the norm? It defines a norm on this M, the space of all n cross n matrices with real entries, and then we'll also see that this satisfies some good relation. So if we have A and B are two matrices, A times B is just matrix multiplication. If we find this norm for the matrix AB, this should be less than equal to norm A times norm B. And this happens for every A, B, N, M, N, R. So first thing first, let's start with the notion of norm linear space. So norm linear space is just a vector space. I'll just recall basic definition of normed linear space. So we denote it as x times x. It's kind of a structure that has a vector space and some norm. So vector space, I hope you all are familiar with the term vector space. Vector space X is said to be a norm linear space if there exists some function which is from x to r plus such that now this function satisfies some specific conditions which are which are motivated. We can say that these properties were motivated by the modulus function. So what's the basic very good properties of the modulus function? First one, it is always positive. That's what happens with the norm. So this is always positive for every x in this capital X. Now this capital X can be any vector space, so that means the small x can be called the vectors. Then we have the property that this is 0 if and only if the vector is 0 itself. Then we have the property of scalar multiplication. Now if we have the scalar multiplication, suppose C is some element from the field, then this is equal to mod C times norm X. So basically, in the context of non-linear space, the field is not given, we assume that the field is either the space of real numbers or the complex numbers. And this happens for every C in the field, which is R here, and X in X. Then again, a very beautiful property of the modulus function, the triangles inequality. So we have triangles inequality in the context of norm as well. So this says that mod x plus y, this is norm x plus y is less than equal to norm x plus norm y. Now if we are able to find such a function defined on this vector space X, then we call that this is a norm-linear space. So let's see whether this M and if M with this norm, whether it is a norm-linear space or not. Okay, so let's start with our first property. Obviously, clearly, this space is a vector space. We all know that. And since we're taking the entries from real numbers, we can consider our field to be R. Clearly, M in R is a vector space on the field of real numbers. Then we start with the first property. We want this to be positive. So how is it defined? This is equal to summation ij 1 to n mod aij square to the power 1 by 2. This is obviously always positive because modulus is positive, square is positive. We are just taking the root, and root function is also positive. So this is greater than equal to 0 for every a in m n r. So first property holds. What about the second? Second says that this is 0 if and only if the vector is 0. Now let's see what happens when this norm of any matrix, this is equal to 0. Now this happens if and only if, now since the root of some number is 0 if and only if the inside one is 0, so this happens if and only if 1 to n mod aij square is equal to 0. Now on one side we have sum of positive real numbers, and on the other side we have 0. So this is possible only if all the terms are 0, because sum of positive terms will always end up into some positive entity. So if any of the aij's were strictly positive, in that case the sum would have turned out to be strictly positive, but this is exactly equal to 0. So therefore this happens if and only if aij mod square, this is equal to 0 for every ij from 1 to n. Why? Because mod aij square, this is greater than equal to 0 for every ij. Now that means this happens if and only if aij is 0. Obviously this modulus of square is 0 or if and only if the value is 0. So therefore what do we get? Now that means the matrix A was actually a 0 matrix. Therefore what we get, this norm is 0 if and only if the matrix is 0. I hope this part is clear. The main idea is this. Obviously the sum of positive terms can be 0 only if all the terms are exactly equal to 0. Next we need to check the property C. So let's see be any real number. What will be mod CA? So firstly, what will be the matrix CA? CA matrix will be just multiplication of all the terms with C. So that will be summation ij from 1 to n C aij square to the power 1 by 2. Now this C square can be taken outside. So yeah, square root of mod C square is just mod C. And what we are left with it is the norm of the matrix A. That's what we need to show. Therefore, the property C also holds. Last one is the triangles inequality. Okay. For that, we will need very good result, which we call the Hilder's inequality. I hope you all are familiar with that. I'll just recall the Hilder's inequality. It says that summation I from 1 to k mod ai times bi, this is less than equal to summation I from 1 to k mod ai to the power p to the power 1 by p times summation I from 1 to k mod bi to the power p prime 1 upon p prime, where p and p prime are such that 1 by p plus 1 by p prime is equal to 1. So this is Hilder's inequality. I hope you must have done this in your high school or previous courses. So we'll be using this inequality to prove this triangle's inequality, and hence we'll get the norm. So yeah, let's see how. Let A and B be two matrices in M and R. So what do we need to show? We need to show that, or else say we claim that this A plus B is less than equal to norm A plus norm B. So let's look at this norm of A plus B. So we all know that adding two matrices means we add coordinate wise. That means each coordinate, suppose C is A plus B. In that case, Cij will be nothing but Aij plus Bij. Sorry, small p. That means this norm of A plus B is summation Ij from 1 to n Aij plus Bij square to the power 1 by 2. That's just coordinate wise addition. So now I can write this as, okay, so this is equal to, or let's start with the square of this term so that we'll deal with this root at the end. Okay, so this is equal to summation Ij from 1 to n mod Aij plus Bij times, yeah, of course I can write A square equals to mod A times mod A. Aj plus Bij. Now we'll use the triangles inequality of the modulus function. So this mod aij plus bij is less than equal to mod aij plus mod bij. So this is less than equal to plus, just splitting the sum because we are in the finite sum scenario. Now we'll use use the Hilda's inequality with taking p and p prime to be equal to 2, because we know that 1 by 2 plus 1 by 2 is always 1. So using Hilda's inequality for p and p prime equals to 2, we get this to be less than equal to summation ij from 1 to n plus summation ij 1 to n bij square to the power 1 by 2 summation ij 1 to n mod aij plus bij square to the power 1 by 2 by using Hilda's inequality for p equals to p prime equals to 2. And this is equal to the norm of A times norm of A plus B plus norm of B times norm of A plus B. So therefore we started with the square of norm of A plus B. Therefore we get norm A plus B square. This is less than equal to, if I take norm A plus B common, we'll get norm A in plus norm B, and this gets cancelled out. We are left with norm A plus B is less than equal to norm A plus norm B. That's our triangle's inequality. So therefore this is a non-linear space. So I would like you to go through this all 4 steps once again, how we are able to show that this space of all n cross n matrices along with this norm is actually a non-linear space. Then we'll see part B, where we deduce this type of inequality. Yeah, please go through it. Okay, so if there is no doubt, we can move ahead. Let's look at its part B. Let A and B be two matrices. Let A and B be two matrices in M and R. We need to show that this norm of A times B, this is just matrix multiplication, this is less than equal to norm of A times norm of B. So let's firstly see the ijth element of the matrix AB. We all know that this is equal to summation k from 1 to n aik bkj. So that gives us this abijth term square. This is equal to summation k from 1 to n aik bkj square. Now this is actually sum of n terms, and then we are taking the square. So we all know that this, if we have x1 plus x2 up till xn square, this is always less than equal to x1 square x2 square up till xn square plus mod x1 x2, and in fact we'll have, yeah, plus I'll write it in summation form. So this will be modulus summation k from 1 to n aik bkj square plus summation, we'll have s and k from 1 to n with s not equal to k, and the terms would be ais bsj times aik bkj. That's just the expansion, and then we have modulus square. So yeah, and then by triangles inequality of the modulus function, I should write this as, so this is aik bkj square. So this will be less than equal to summation k from 1 to n mod aik bkj square plus summation s k from 1 to n with s not equal to k mod ais bsj times aik bkj, and therefore this norm of ab square, which is equal to summation ij from 1 to n ijth element of ab modulus square, and this is equal to, if I mark this as equation 1, so by equation 1 this is less than equal to summation ij from 1 to n summation k from 1 to n aik bkj square plus summation sk from 1 to n with s not equal to k mod ais b. bsj times mod aik bkj. So this, yeah, I'll write that. This is by inequality 1, and this is equal to summation ijk from 1 to n mod aik bkj square plus summation ijk from 1 to n with s not equal to k ais bsj aik bkj. Okay, so therefore I'll mark this as equation 2. Now let's see the right hand side of the inequality. Now this norm a square times norm b square, this is equal to summation ij from 1 to n aij square to the, yeah, just a square times summation st from 1 to n bst square to the power 1 by 2, not 1 by 2 because we're taking square. Okay, if you just open this up and use the distribution property of the real numbers, this will eventually be equal to summation ijst from 1 to n aij bst square. Now this, we can split this sum as summation ijst from 1 to n, where j is equal to s aij bst square plus summation ijst from 1 to n, where j is not equal to s mod aij bst square. Now since j is equal to s in the first term, we can replace j and s both by some other variable, say suppose k. So we can write this as summation ij k from 1 to n mod ai, not j, yeah, j and s, both j and s are replaced by k, no? So this is equal to, in fact, okay, this is equal to I k t from 1 to n mod aik bkt square plus summation ijst from 1 to n j not equal to s mod aij bst square. Okay, and also in first term, just for the notational similarity, from because we want to use equation first, in this case the common term here, this was k and ik kj. Just to make it similar, we can replace, t is just a variable, we can replace this t variable by j. So this will be equal to summation ij k from to n aik bkj square. So here we have taken js to be k, and here I have taken this t to be j, just the notational change. And this is plus summation ijst from 1 to n, where j is not equal to s, mod aij bst square. Now something like this is already present in our inequality second. If we use this, we get this term is greater than equal to norm ab square minus this term. So this will be greater than equal to norm ab square minus summation ijst from 1 to n, where j is not equal to s, mod ais bsj ait btj. Also we had the second term summation ijst from 1 to n with j not equal to s, mod aij bst square. So by equation 2. I hope till here it is fine. Then now if it let's see this term, this one. Let's mark this as equation 3. We will get back to equation 3 before let's analyze the extra terms, because basically what do we want? We want norm a square times norm b square to be greater than equal to norm ab square. So basically we want the rest of the term to be at least greater than equal to 0, so that it gets removed. So let's see, denote some other constant s to be summation ijst from 1 to n, j not equal to s, aij bst square minus summation ijst 1 to n, j not equal, sorry, s not equal to t. I did something. It was s not equal to t. Oh, yeah, when we called this inequality 2, this was the second term was s not equal to k. And since I am writing t instead of k, it should be s not equal to t. Sorry, s not equal to t. This is ais b bsj ait btj. So just for notation, simplicity, let's denote this t by j, this j by t. So what do we get? This is equal to summation I j s t from 1 to n, mod a I j b s j, a I t. Yeah, just uh, replacing them. Minus summation ijst from 1 to n with s not equal to t ais btj. Yeah, we can write this as like this. Nothing half bsj. Okay, now I'll take the summation over ij to be outside, because in both the cases we are taking from ij from 1 to n. So this is summation ij from 1 to n. Then inside we have st from 1 to n. This is with s not equal to t, with s not equal to t mod ait bsj minus summation st1 to n s not equal to t mod ais btj times mod ait bsj. Yeah, so this is equal to summation ij1 to n. Inside we have summation st1 to n with s not equal to t, and this is equal to mod ait bsj minus mod ais, yeah, we had square now, btj whole square. You can just expand it and get exactly the same thing. Yeah. Okay, then this is equal to summation ij1 to n summation st1 to n with s not equal to t mod ait bsj minus ais btj whole square. This is always positive. That's what we want. Okay, therefore s is greater than equal to 0. Okay, now since by equation 3 we had norm a b e square is greater than equal to, this was, sorry, norm a square times norm b square. Norm a square norm b square, this is greater than equal to norm ab square plus s, and since this s is greater than equal to 0, this is greater than equal to norm abe square. So taking square root on both the sides, we get norm abe is less than equal to norm a norm b. This is what we wanted to prove. And this is what we call the yeah, let's leave that. Okay, so I hope this is fine with everyone. If you have any doubt at any step, you can ask how we got this inequality. In fact, I think this summation and all is quite complicated. That's why it would be good if you write it yourself, see each step how we are getting. If you have any doubt, please ask. I'll wait for 5 to 10 minutes. Okay, so if there is no doubt, we can end this session. So we'll meet. Yeah, okay, so we'll meet next Saturday. Thank you.